Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a very nice homemade system of equations with complex numbers. So we have z to the power w, which is equal to zw, which is equal to I. And we're going to be solving for, guess what? Z and w. So we have this interesting equation, and I called it a system because you can write it separately, right? So we can write it as z to the power w equals I and zw equals I. So let's go ahead and do that and see the system as a system. Z to the w equals I and zw equals I. And I'll try to present two methods here. Let's go ahead and take a look at them. So for my first method, I'm going to go ahead and work with the first equation first, okay? Z to the w equals I. That's going to be my main focus first. So we have something called a complex exponential. By the way, if you're new to complex numbers, go ahead and check out my lecture videos. If you like algebra, number theory, and trigonometry problems, go ahead and check out CyberMath, which is another channel of mine, my very first channel. It's cyber with an S. And if you come from there, say hi. Great, so how do we solve this using a complex exponential? Z to the w can be written as e to the power w ln z. And if you kind of think about it, this makes sense because bring the w over here, you're going to get e to the power ln z to the w, which is basically z to the w, right? So this is what z to the w equals, and we know that it's equal to I. But now we want to use the polar form of I, which is using exponentials. Thanks to Euler, we have the polar form of a complex number, and it can basically be written as using two things. One of them is called the argument, which is the angle or the theta, and the second one is the absolute value of z, which is also called r. It's also called modulus. Okay, the distance from zero. And of course, if I say absolute value of z equals a constant c, that is the equation of a circle. So complex numbers are actually really nice because you can really write the equation of anything in a very compact way. So this is called the real axis, this is called the imaginary axis, and the whole thing is called the Argand diagram. And Argand is spelled like this, so don't get me wrong. Probably the name of the person who discovered something like this. Anyways, now, how do we use that information? Well, if a complex number can be written like this, using a little bit of trigonometry by using the absolute value as well, you can basically write a complex number as r times the quantity cosine theta plus I sine theta. But again, thanks to Euler, he discovered that, hey, this can be written as e to the power I theta, which is, by the way, the most beautiful equation in math because it's just beautiful and because it's Euler, right? So compact, isn't it? Now, using an exponential, and obviously, this makes raising a complex number to any power a lot easier because you can just raise it by using exponentials. Like, let's say you want to raise this to the fifth power, it's just going to be e to the power 5I theta with r to the fifth. Does that make sense? It's super duper quick. And by using that, you can also find an expression for cosine 5 theta and sine 5 theta, as well as any other multiples of theta. But this is critical. And what this means is actually e to the I theta is equal to this. Great. And now, how do we use that information to write I? Well, if you think about I is actually 0 plus I. So as a point, it's going to be at 0, 1. And of course, its distance from the origin is going to be 1 unit, so I can be written as 1 times e to the power I pi over 2. Of course, pi over 2 is the argument, the angle that it makes with the positive real axis, but that's not the only angle. It's just a principal argument because that's the smallest between negative pi and pi. And if you wanted to expand on this, you can add like a multiple of 2 pi to it, or you can subtract from it as long as you are using integer multiples of 2 pi. What is that supposed to mean? We can actually write down or add a 2 pi n here, where n is an integer. Positive or negative doesn't matter, okay? But to keep things a little simpler, let's just use the very principal value of I, which is e to the power I times pi over 2. This is going to make our life a lot easier. If you want to proceed with more complications, go ahead and do so. But now we have z to the w equals e to the power w ln z, which is equal to e to the power I times pi over 2. Beautiful. Now, this means, again, I'm ignoring multiples of 2 pi here, but it just means that these two things are equivalent. So w ln z equals I times pi over 2. Isn't that awesome? Now, take a look at this. Some of you will probably recognize what's on the right-hand side, but let's not talk about it right now. Let's go ahead and use the second equation, which gives us zw equals I. I can also write it as wz equals I. Guess what happens? We can divide these equations, and ta-da! Interesting things happen. W cancels out, I cancels out. You end up with a single variable, which is actually the purpose, by the way. On my other channel, I made a video about a system of differential equations, and I'll try to continue to do that, hopefully once a week. Let me know what you think about the problem. I think you liked it overall, based on watch time, I can tell. But if you haven't checked it yet, go ahead and check it out. I'm also going to share a link down below. But let me know what you think. So we ended up with this equation. Why was I talking about the differential equation system? Because over there, we kind of use a similar idea too. Not particularly for this problem, but anyways. Let's get back to this. So what does this equation tell you? It's in z only, which is good. So with most systems, you basically want to get rid of one of the variables so you can reduce the number of variables. If you have a system of 3 variables, then you want to get down to 2 first and then the 1 so that you can solve it, right? Because you can't really solve for 2 variables at the same time. Unless you're looking for something like x plus y plus z, right? That's a different story. Now, for this one, you can kind of think about how you're going to solve this. And I know some of you already recognize the pattern here, but I'm going to talk about a very special pattern here. Let's go ahead and talk about it. First of all, 1 over z times ln z. This is what we can write it as. And then 1 over z means z to the power negative 1. I make my z's like that so you can tell the difference between a z and a 2 and a 7. Actually, 7, my 7s I make like this. So you can tell, and z's are different too. Anyways, so this is equal to pi over 2. But here's the thing. I have z to the power negative 1, but I don't have ln z to the power negative 1. But that's an easy fix. Let's go ahead and multiply both sides by negative 1. And then this is going to bring in a negative sign here, right? And then I'm going to take that negative, put it up here, because that's the property of logarithms, right? One of the properties. You should know that. It's the power property, and this gives us a new equation, which is much better than the original one because now we have z to the negative 1 and z to the negative 1. If you wanted to use substitution, you can definitely go ahead and check, set it equal to something. But that's not what I'm going to do. I'm going to use the identity. I'm going to write z to the power negative 1 as e to the power ln z to the power negative 1 because as you know, e to the power ln y is y, and don't ask why. So this gives you e to the power ln z to the power negative 1 times ln z to the power negative 1 equals negative pi over 2. Awesome. Now, what do we have? If you bring the ln z to the power negative 1 here, and then write the e to the power ln z to the power negative 1 after that, and set it equal to negative pi over 2, this is basically going to give you what you're looking for. And what is that? Let's go ahead and call this u. This is going to give you u times e to the power u. And what is that supposed to mean, right? Well, like I said earlier, this is a special pattern. We're going to be using a special function called Lambert's W function. Okay, are you ready? So let's go ahead and W both sides. And what Lambert's W function does is it just takes a product like this. Oops. It just takes a product like this, u times e to the u, and turns it into u. It's also called product log for a good reason, because if you take e to the u and ln it, you get the u, but this is a product. So you turn from a product, you turn the product into u, which is the argument or the independent variable in this case, okay? So this gives you u, okay? U is equal to w of negative pi over 2. Okay, great, but how do you find w of negative pi over 2? That's a good question. Now, we're going to go ahead and work on that next. So for that purpose, let's go ahead and leave this here. And I'm going to go ahead and work with negative pi over 2 until I bring it to a desirable format. So first thing I'm going to do is write this as negative 1 times pi over 2. And then replace negative 1 with I squared. Uh-oh, I forgot to say that again. I squared is negative 1 because I is the square root of negative 1. Something that you should never, ever forget, okay? But I forget saying it all the time. Okay, I squared is negative 1, so I can replace negative 1 with I squared, which is not a very common thing to do, by the way. I got to tell you, it is very common to replace I squared with negative 1, but not very common vice versa, okay? But you got to do it in this case because it's going to make your life easier. And then what do? We kind of split it up into I times I, or I times I pi over 2. And then I want to write it this way. I times pi over 2 times I. But now I want to turn this I into its exponential form. And remember, I already told you that can be written as, let me go ahead and put these two together. I pi over 2. And now I'm going to replace I with, remember what it is? E to the power I pi over 2. And this makes everything a lot easier. Hopefully this makes sense, right? Now, I'm going to go ahead. I started off with this, and I ended up with this. Can you imagine they're equal? So I'm going to go ahead and put it back here. So now we have U equals W of negative pi over 2, which is I pi over 2 times e to the power I pi over 2. Again, by using Lambert's W function, this is going to turn into I pi over 2. So U will be I pi over 2. But wait a minute, we were not looking for you. We were looking for him. No, her, them. No. It's not that. It's the letter U. We're not looking for you, but we need to back substitute. What is U? U is ln z to the power negative 1. Great. Ln z to the power negative 1 equals I pi over 2. And from here you can say, z to the power negative 1 is e to the power I pi over 2 by using logarithms, the definition of natural log. And from here, you get I, because remember, we talked about this several times, e to the power I pi over 2 is I is e to the power I pi over 2, in a sense, right? So now we got the following, z to the power negative 1, which is 1 over z equals I. And from here, z becomes 1 over I or negative I, because the reciprocal of I is its conjugate, because the modulus is 1. Think about what I said, but the answer is negative I. That seems to be the only solution, right? But go ahead and check out the other branches, which means add 2 pi n and see what happens with what you find. I'm also going to show you, if I don't forget, the result from Wolfram Alpha, which is an LLM, right? I guess when I called it AI, some people said, oh, no, it's not an AI. It's a natural language model or something like that. Okay, fine, whatever. Whatever you want to call it, AI or LLM, we're going to look at the results, see if they can beat humans so far, right? Now, z equals negative I, and then we have the other equation. So what do we do with this, right? What do you do with this information? Well, we found z, so shouldn't we be able to find w from here? Yeah, absolutely, because zw is equal to I. Obviously, that's a lot easier to use, by the way. We know that zw is I. If z is negative I, that means w is negative 1. Wow. That's interesting, isn't it? Okay, so W is real, Z is not real, and that's perfectly fine. Now, what could be an alternative solution for an equation like this? Let's go ahead and take a look at an alternative, right? So here's the original problem, and we're trying to look for something different. Well, one thing you can do here is you can actually isolate W from here and write it as I over Z. You can bring it over here and write it as Z to the power I over Z, and then you can kind of proceed with that. Or you can actually isolate the Z from here and then write it as I over W, and then replace the Z with that I over W to the power W, and you can definitely proceed with that. And let me know what you find by doing that. Okay? Great. You could also do the following, I think. I don't know if it's going to give you anything different. You can divide both sides by Z, and that's going to give you Z to the power W minus 1 equals W. So from here, Z becomes W to the power 1 over W minus 1. How nice, right? And then you can try to plug this in, and you'll probably get something similar. Okay? Let me go ahead and show you what Wolfram Alpha provides for you, the big, gigantic LLM. as opposed to humans. Ta-da-da-da! Isn't that awesome? This is what Wolfram Alpha has to offer. It's amazing, isn't it? And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time in another video. Until then, be safe. Take care. Don't forget to check out CyberMath, the short channel. I have a short channel too. And aplusbi. And bye-bye.